about $100. As for the solder goes, use a rosin core solder. If you use a rosin core, there's really no need for flux because the rosin core is exactly as it sounds. The core of the solder is hollow and it's filled with rosin. So rosin is a type of solder, so it's like killing two birds with one stone. When you use this, it'll melt the solder and then the rosin will come out and kind of like flux the solder and help it melt really quickly. Solder contains small amounts of lead, so you don't want to be breathing in that smoke. I highly recommend using some kind of exhaust extractor or even just a simple fan to blow the toxic fumes from your face. A small solder job's not going to kill you, but it'll give you a nasty headache for the rest of the day. Enough about equipment. Tip number 1. Start with a clean tip. A clean tip will transfer heat much better and give you a cleaner joint. Simply just take a wet sponge or a coiled wire ball and just wipe the excess solder off. Or if you're in the field or in a pinch, just give it a nice tap on the table to remove the excess solder. Tip number 2. Use a cone tip rather than a wedge tip. I feel like the wedge tips are great for batteries, okay for medium-sized wires like motors, but they're really hard for small wires like FPV wires. But the cone tip are good for motors, good for batteries, and really good for fine wiring. I just feel like the cone tip are just an overall more versatile tip to use. Tip number 3. Pre-tin all wires and pads before soldering. It'll make everything so much easier. Melted solder bonds to solder instantly, much faster than solder to wire. Tip number 4. Use high heat. What destroys battery pads is the amount of time on the pad versus the amount of heat on the pad. 800 degrees works well for battery cables all the way down to small tiny FPV wires. But if your soldering iron can do 850, 850 is best for big fat battery cables. Tip number 5. Use the shortest amount of time possible. Using high heat will let you melt the solder quickly so you could get the job done quickly. Just remember, you want high heat for a short amount of time, not low heat for a long period of time on the solder pad, because that's what destroys solder pads. Tip number 6. Soldering small tiny wires like FPV camera wires. Make sure the pad and the wire are pre-tinned. Melt the solder on the pad, then just quickly push the wire into the melted solder. Remove the heat and hold the wire steady until it cools. Tip number 7. For medium gauge wires like motor wires, it's similar to small gauge wire. Pre-tin the wire and the pad. Melt the solder on the pad, then place the wire where the melted solder and the tip meet. When the solder melts, remove the iron and hold the wire still until the solder cools. Tip number 8. Big fat battery cables. This is the one that scares the most people, but it's really not that hard. It's similar to the medium gauge wire. You pre-tin the wire, pre-tin the pad, you melt the solder on the pad, and then you just put the wire where these melted solder and the soldering iron touch, and then you just wait for the solder on the wire to melt. Once it melts, you want the entire ball of solder to be liquid, and then you remove the heat and you wait for the solder to cool without moving the wire. Tip number 9. A solder joint that doesn't have enough solder can come off the pad. A joint that doesn't have enough solder will look bumpy, or you can see the strains of the wire. To fix this, just simply add more solder. Tip number 10. A solder joint that has too much solder is not a good thing either. A joint that has too much solder will look big and blobby, or you'll see like these spikes coming off the solder. To fix this, use a solder wick to remove some of the solder, or just take a hot soldering iron and wipe away some of the solder.
Sizes of beveled edge tip. I generally don't really like the conical tips, which is the pointed type, which is a shame because most soldering stations come with a conical tip as standard, and some of them only have the option for a conical tip. There's no bevel tips even available for them. So this is one of the things I really like about the Hako. So when it comes to the temperature I use for my soldering station, I generally set it at around about 400 degrees Celsius, which is about 750 degrees Fahrenheit. Now, the melting point of leaded solder is about 180 degrees Celsius, so 400 might seem a little bit high. But the thing is that I'm not just looking to melt the solder, I'm wanting to be able to transfer the heat from the soldering iron to whatever it is that I'm soldering. So that's why I have that temperature a bit higher. If I was working with lead-free solder, I'd probably be looking at about 450 degrees C or 850 degrees Fahrenheit. I'm not super fussy about it. Near enough is good enough for me. Okay, so I've got my little soldering. The purpose of flux is basically to help with the stopping the oxidization process, or oxidation process, depending on which part of the world you're from is oxidized. So flux basically helps in that process by stopping the oxidization of that metal on the soldering iron or on whatever you're soldering to, so that that solder will then adhere much easier. Now having said that, the leaded solder has a slightly lower melting temperature, so it can actually be a little bit easier to work with, and that's one of the reasons why I do tend to work with leaded solder, though I am trying to wean myself off it. So if you are going to be using leaded solder, it's very important that you have lots of really good ventilation. I've got a little sort of air filter. It's not the best sort of air filter, it's better than nothing, but one of the things I tend to do is when I'm working, I've got a fan here behind me. Let's get a little bit more. Okay, now I'm just going to just give the wire a bit of a twist like this, so that just holds those little bits of wire, the little pieces of wire together there. Okay, so now I want to join these two wires together. Now you might just say, okay, we'll put those two wires together and dump some solder on them. That's generally not what I do when I'm soldering items like this. What I like to do first is I like to get solder on the two things that I'm planning to join, and then I melt them together. So let's start off with that. I'm going to just put this wire into the holder, and I am going to, there we go, got that nice and in focus. I'm then going to get some solder onto this wire. Right, now here's one of the most important parts of the technique, and this is the mistake that a lot of people make when they're first starting out with soldering. And the mistake they make is that they melt the solder onto the tip, and then they try and transfer that solder onto the wire. That is absolutely not the way to do it. What you need to do, and this is where that flux that's inside the solder is really important, because that flux that's inside the solder only works at the time that it's melting. So once you melt it onto your tip, that flux it's done its thing, and it's of no use to you anymore. So you actually need to make sure that flux is being used when the solder is melting. So what you need to do, the correct procedure, is to use the soldering iron to get the wire hot. So this is, you're using the actual soldering iron to get the wire hot rather than melting the solder. Let me just clean this tip a little bit, it looks a little bit ugly. Okay, so I'm going to put him on there, and then what you do is you use the solder, then melt the solder onto the wire, not onto the tip. As you can see, that burning, that smoke coming off, that is actually the flux, and that's showing you that that flux is doing its job. And so as you can see now, that wire is completely coated with solder. Even if it is a little bit out of focus, it's completely coated with solder, and that's ready for us to do a join. So let's go through and do that one again with the other wire. So let's grab this second wire here, and again, let's get that all nice and in focus as best as we can. Once again, soldering iron goes to the wire, gets the wire, tries to get the wire as hot as possible, and then melt the solder onto the wire. There we go. And then any excess that you end up with on the tip, you're just going to clean that away with your little tip cleaner, little mesh tip cleaner there. So now we've got two pieces of wire that have both got solder on them. Here we have two wires ready for joining. They've both got some solder on them, so I don't really need any more solder. But if I wanted to, I could just grab some here at the same time to melt them. And then I've grabbed the wrong soldering iron again. Let's try this one. And then we apply the heat to the area and then just melt those two together. There we go. Look at that. Okay, so obviously making sure that it cools. Don't pull them apart too early, otherwise the solder won't have cooled. But here you can see that that's cooled and it's solidified, and we've now got a nice, neat and tidy join there. And you're not hard, but just gently grab this wire, pull it a little bit, and bend it. And then grab this side, pull it a little bit and bend it. And those bends are now stopping it from falling out. So that's going to stay in place while we do the soldering. So, and there's our little wires that are bent there. So let's jump back now to the microscope and we will have a look. And there's wire number 1 and there's wire number 2. And I am now going to just solder these wires in place. So we'll start with this one. Grab my trusty soldering iron and again applying the heat to the components you want to solder to and then melting onto those components. Now this is really where I was referring to the difference between a conical tip and a beveled tip. Now if I show you a bevel tip, I'm going to show you a great big bevel tip, but it's just for the purpose of demonstrating. So this is a bevel tip here, and you can see that you've got this great big flat surface. And what I like about these is you can apply them like this and apply a large surface area of heat down onto any board that you might be working with. But with the fine point tip like this one, you have more trouble getting the heat where you want it to go. Now what you could do is you can maybe lie this down so you get a little bit more surface area of the iron onto what it is you're trying to solder to. So anyhow, I'm just going to hold that there. That's applying some heat to the pad and to the wire, and then just going to grab this and melt, and melting onto the pad and onto the wire, and there we go. And as you can see, we've got a lovely, neat, clean, tidy little blob going on there. And then just a matter of clipping the excess of that wire off. So that's that. And there you have a lovely, clean solder joint going on there. We hold that onto the copper pad, and we're holding it onto the wire as well to try and transfer heat to both. And then we just get the solder, we melt that, it's melting onto the pad and melting onto the pin as well. So
the oxidation happens because we live in an atmosphere that contains oxygen, and the metal we are trying to solder has a surface that likes to bind oxygen atoms. This layer acts like a barrier to whatever two metals you are trying to join, either by soldering or even welding. So for soldering, the oxide layer must be removed so the solder and metal can come into direct contact. And something must be added so when the metal is heated, no oxidation forms. Here's an example. This is a bit of multi-stranded wire, nice and shiny. This will solder great. Here's some copper pipe. It's dirty and is heavily oxidized. It will need to be sanded to get down to the clean metal, so it looks like this. This is a strip of brass. It will solder great with the correct soldering flux and the correct heat applied. This is some heavily oxidized brass rod. It will not solder without first being cleaned up like the copper pipe. So what's an appropriate soldering flux? This is your typical 60-40 rosin core solder. It contains 60% lead and 40% tin, and turns liquid at about 370 degrees Fahrenheit. The rosin core works as a shield to prevent oxidation while soldering. This solder is designed for use in electronics, mainly soldering wires. I use it on circuit boards and pretty much anything electronics related. I also use this type of resin flux to help flow the solder when the rosin core in the solder is just not enough. As solders go, it's not very strong, and it contains lead. Here is some lead-free solder. This is often used to solder copper pipe used for plumbing in buildings. The lead-free part is important, as the lead in leaded solder will slowly leach into the water flowing through the pipes. This solder is also stronger and has a higher melting point than leaded solder, about 422 degrees Fahrenheit. One drawback to lead-free solder is that the correct flux contains acid to help strip the metal of oxidation at the higher soldering temperature. This works fine, but it must be cleaned off after soldering, or corrosion from the acid will result over time. Never do this. Solder wires with acid flux. It makes a nice solder joint all right, but the flux is now leached into the wire, and over time the wire will corrode invisibly from within inside the insulation. Together. A little ESC speed control for a model airplane I had, and this is just out of one of my junk boxes. I'll use it in a future project. It got taken out of some other project long ago and got the plugs cut off of it. So I need to solder on a little wire extension and put a plug on there. So the first step is getting some insulation off the wire. I do that with some little wire strippers. Now that we have both stripped, I always like to wind up the braids of the wire a little bit so they don't just flail around and stick out when you go to solder it. This seems to help a lot. So for soldering these wires, I'm going to use 16th inch diameter rosin core solder. It's the 60-40 blend. It's probably the most common type of solder for soldering electrical connections. The soldering iron is hot, and looking at the tip, you can see that it's not bright and shiny. That's because the little bit of solder that's on there is oxidized. So to make good solder joints and be able to solder easily, we first need to clean the tip and then tin it. So I do that in one of these little steel wool things or brass wool things. And you can see it's already much more shiny. I got the oxidation layer off of the solder, and then we tin it a little bit more solder. And I got some rosin core on there, and I'll shake it out to get the blob off the end. So it's ready to go. So the first step is to tin the wire. And we do that with just a little bit of solder. So I have my other piece of wire pre-tinned. But I want to put a little bit of solder on the soldering iron so that when I bring in the other piece, I have a little bit of extra solder to solder the two wires together. And there we go. So that's a good solder joint. You can see that the solder is fully connected, both pieces of wire. It's shiny, it's not oxidized. And I could have had my wires a little bit more parallel, but this will be fine. So now I've got both wires soldered. The black turned out pretty nice as well. That's a good strong solder joint. Now these two wires are going to be plugged into a LiPo battery, so having two exposed wires touching each other is extremely dangerous and will eventually cause the LiPo battery to explode and cause a fire and possibly burn down my house. So I want to insulate these wires in a professional manner. So we'll insulate the wire with heat shrink tubing. I have a whole selection of this stuff ranging from diameter smaller than this all the way up to about 1/2 inch. It's great for insulation. Cut off about a 1/2 inch of each piece and thread it down the wire and over the solder joint. At this stage, you can use a soldering iron to shrink the heat shrink onto the wire, but a much better solution is to use a heat gun. So there we have it, 2 insulated wires, ready for a plug and connection to a LiPo battery. So here's some 24 gauge wire, it's pretty small. And again, the first thing we do is wind up the strands so that they hold together. So for soldering small diameter wire, I use small diameter solder. This way I don't end up with a giant blob of solder on the wires I'm trying to solder together. Pre-tin the wire. Over the years I've developed the skill of being able to hold two pieces of wire in one hand and solder with the other. I consider it my superpower. That's a good solder joint. So here's some 10 gauge stranded wire. My little 30-watt soldering iron really wouldn't put out enough heat to make a good solder joint, so I've got to move up to the next size tool. So as before, I'm pre-tinning the soldering iron, putting a little bit of solder on there. I'm not using that solder to try to fill up and tin the wire. I'll add more solder to the wire and let it flow in. That way it gets solder and resin core all the way through every strand in the wire, and that'll make a strong solder joint. Okay, let's do some PC board soldering. This is a through-hole device. It's called that because, well, the pins go through the holes. On these devices, I like to bend over the corner pins, just 2 of them, so it doesn't fall out while I'm soldering. And there it is, just the right amount of solder. The solder is nice and shiny, so I know I don't have any cold solder joints. And how about some surface mount? First, I like to spread a little bit of rosin flux on the board where the part's going to go. It really helps the solder to wet out and not form cold solder joints.
Have your solder ready. The soldering iron should be set between, say 300 degrees C and 350 degrees C to start. You'll find that that's a very comfortable range just to be working in normally. For some applications, you might need to bring that a little bit higher, and we'll talk about that here in just a little bit. So the reason that you need to have some solder ready before you turn on your brand new iron is if the tip of your brand new iron remains dry, so no solder on it, you will greatly, and I mean greatly, reduce the life of that tip, and you don't want to do that. In normal service, what you do is you take it, you clean the tip off like this, so get rid of the solder. You can use one of these cleaners as well, whatever you're comfortable with. Then you'll start doing your work, so you'll start doing your soldering, and then when you're done, before you put the iron back into the holder here again, you want to re-wet the tip, make sure there's lots of solder on it, put it back in the tip, and you're good to go. This is a necessary step, and when you're soldering something with a plated through hole, the dwell time of your soldering iron, so the dwell time is the amount of time that you keep the iron on the trace. So the dwell time has to be just a little bit longer because the solder has to not only flow on this side, it should flow through the hole around the lead of the component. So that way you're not only just relying upon this little solder connection here, but it's soldered right through the barrel onto the other side of the board. That just makes a good solid connection, especially in rework. Now it's quite a fine balance when you're soldering. If you have the iron on the board too long, you'll cause these things to lift off the board, and you don't want to do that. So having your soldering iron temperature right is very important. So when I'm soldering these boards, again, my soldering iron is between 300 and 350 degrees C, and it seems to work just fine for these plated through holes. So in order to solder a component on here again, we want to clean the tip of our iron, make sure that there's nothing on it. We would come in like so, and we're just going to touch the iron here like this. And you can see how nicely that flows around there. And we have a good connection there. So if I was to solder this other one here, you can see that there's nothing in there. It'll just fill the hole at this point. Let's give you an example here. You can see it'll just start to fill the hole. See that little hole? It's going down through the hole. Now, if you've pulled a plated through hole out, if you've pulled that little barrel out of the center, it won't do that. The solder will just sit on one side of the board, and it won't connect to the other side of the board. And again, in any kind of reworking, you have to be very, very careful that you don't pull on the component. You really need a decent desoldering tool. And again, we'll do a desoldering video as well here in the very near future. I'll show. So I'm going to add just a little bit of solder to this tip right now, right about here, just like that. Now this solder really doesn't take all that well. So now what I'm going to do is add flux to this. This is very important for any kind of surface mount work, especially rework and anything like that. Don't rely upon the flux in the solder or you're going to have a really rough time. So just smear it around with this. So then what you do is align the component up with the pads, just like so. Try and get everything about as centered as you can. What I usually do at this point is I just touch the top, give it a bit of a push to make sure that it's right down. Now the solder that's on the tip will get wicked up because of the flux on the pad here. So what I'm going to do is just touch the pad, and you can see that it's pretty much wicking it up and pulling it onto the surface. Now I can let go of this, and that's completely soldered at that point. So now I can move this around and make the solder connections quite a bit nicer. So I'll clean this off, and I'll just come in here like so. You can see how nicely that solders now. Come in here like so, and work my way around the device. Now, if you're working on a larger circuit board, sometimes it's not this incredibly easy to get in here and do your soldering. You go and touch that last one up. And there it is. It's soldered on. So this is just a little gate that I've soldered on here. Now what I would end up doing is, again, for this board, I would use lacquer thinner in a well-ventilated area and just clean off all the flux. And I can look through this area here to make sure that there's no connections or anything like that. So I've got the focus fixed right now because this is such a small device. I don't want this thing to wander. But at any rate, there is no connections in there. That's pretty sound. Everything is good. At any rate, if I was to shine light under here, I would look between the leads just to make sure there's no little solder balls or anything, but I can even see on camera that it's a nice clean Nice clean job. And that's how you solder components on surface mount components onto a circuit board. What I'll do is I'll get another little circuit board here and I'll say solder on a.
For this kind of small electronics project, you can set the soldering iron temperature to around 325 degrees Celsius. This is hot enough to both melt the solder and heat up the solder pad and the component leads that you need to bridge together. Before we install the first component on the board, which will be an LED, let's take a look at what a good solder joint looks like. In this example here, what you see is the iron is applied to one side of the solder pad on the board and the leg coming out of the component, and the solder itself is fed to it on the opposite side. In other words, the goal here is to heat the component leg and the solder pad, not the solder itself. Heat the work, feed the solder. And that starts with this red LED. Make note that LEDs are polarized. Say for example, the longer leg on the LED is the positive side, and the shorter leg on this LED is the negative side. And you can see these through holes for this LED are marked as positive and negative. The long leg goes to positive, short leg to negative. You can also match up the polarity of an LED by matching the flat side of the LED to the flat side in the circle on the screen on the circuit board. Once you have the LED leads lined up with the through holes, push the LED through. Then on the back side of the board, spread the two leads apart from one another. This will help hold the LED in place while you solder the leads in. Before you start the soldering, and especially with a brand new solder tip, you might find it helpful to do what's called tinning the iron. You just apply a little bit of the solder directly onto the hot tip. This can make it a little easier when it comes time to feed the solder into your solder pad and your connection leads. Now to solder everything together, just touch the hot iron to the solder pad and component lead on one side and feed the solder in from the other. Then switch to the other lead and repeat the exact same process. Hot iron to the lead and solder pad, solder fed in from the opposite side. Once you have the leads soldered in, you'll need to trim the excess lead from the components. Just lift the leads up, grab your flush cutters, and trim both of the excess sets of leads. Resistors are meant to restrict the flow of electricity through a circuit. The color bars indicate exactly how much resistance they have, and the gold band indicates the tolerance or how accurately the resistor is rated to do its job. Resistors are non-polarized, so you can insert them in either direction, but if you want things to look pretty, you can insert them with the color band facing the same direction for each resistor wherever possible. Once it's inserted, just bend the legs to the sides to hold it in place. Then it's just a matter of the same soldering technique. Heat the leg and the pad, feed the solder from the other side. And like before, once your soldering work is done, grab the flush cutters and trim the excess leads from the bottom of the circuit board. Then flip the board back over once you're done. The kit comes with a switch and is just used to turn the board on and off. Enough said about that. The switch has 6 legs on it and is meant to be oriented with the switch facing the outside edge of the board. Just like with the push button, you'll make this job a lot easier if you use some Kapton tape and tape the switch into place. With the switch taped down and secured, flip the board over and you'll have access to the leads and soldering pads. Don't be afraid to rotate the board in order to gain better access to the leads as you do your soldering work. Flip the board over, remove the tape, and the switch is ready to go. With the resistor knocked out, let's install the PIC chip. PIC stands for Programmable Interface Controller, and it's just another way of saying it's a chip that carries out a set of instructions. Take note that the PIC needs to be specifically oriented with the circle on the PIC facing down toward the bottom of the board. The circle indicates where the number 1 pin on the chip is located. You might also see a notch at the bottom of the chip, which you can match up to the notch silkscreened on the board. Once you have the orientation set correctly, insert the chip into the board. As the legs here are short also, you'll probably want to use that Kapton tape and tape it into place. Then flip the board over to access the solder pads and the leads. Just like all the other components, don't be afraid to rotate the board if you need to get better access. And if you find residual flux laying around on the board where you soldered but it didn't burn completely off, just use a Q-tip and some isopropyl alcohol to clean off the area. Once the PIC is soldered in, flip the board back over and remove the Kapton tape. Surrounding the PIC on this board are 3 ceramic capacitors. These types of capacitors are normally used to help regulate current as it flows through a system. Just like with resistors, they're non-polarized and can be installed in any direction. Simply insert the 2 leads from the ceramic capacitor into the 2 through holes on the board. Then flip the board over and bend the 2 leads from the capacitor off to the side to hold it in place. Just like with the other components, heat the solder pad and lead on one side and feed the solder in from the other. Generally speaking, you want to try to keep this operation down to about 5 seconds or so. Then bring in the flush cutters and trim the excess lead from both sides of the capacitor. Then flip the board back over, and it'll give you the opportunity to inspect your work. Diodes act like a one-way gatekeeper for current. They allow current to flow easily in one direction, but inhibit current from flowing in the opposite direction. Diodes are polarized and can only be installed in one direction. See the black band on this diode? It indicates the direction that current flows out of the diode. And the board indicates where the black band belongs between the two solder pads in the diode location. Insert the two leads from the diode into the two solder through holes with the band facing to the right. Flip the board over, and just like before, you can take these two leads and bend them side to side in order to hold the diode into place. And just like with the other components, heat the work, not the solder. Put the iron on one side with the pad and the lead, and feed the solder in from the other side. But that's where the batteries come in. That battery case that came with your kit actually has two wires that feed underneath through these holes and up to the battery terminals at the solder pads. The fancy name for it is called cord strain relief, but it basically just stops the wires from getting yanked away from the solder pads. Feed the red lead through the left side where the plus is located, and then feed the end of the lead into the solder pad for the battery terminal here. Then repeat this process with the negative lead going through on the right side and into the solder pad. Then flip the board over so that you can solder the two leads in. You don't have to do any solder work where the wires run through the cord strain relief, just solder where the two leads meet the two solder pads. And if you need to do any cleanup work, soak a Q-tip in isopropyl alcohol and just lightly scrub the area to clean up any residual flux or other things that need to be cleaned from your solder work. And if you have any extra lead from the battery wires coming through the solder holes, you can grab the flush cutters and just trim it flush. Just be careful to trim the lead and not the solder itself, or you'll be resoldering the joint. Then flip the board back over, and before you put the iron away, and as needed, clean the soldering tip with a hard cleaner like this or a wet sponge. Joints and bridge solder connections. I've done my best along the way to replicate these problems so that you can see them and see what the solution is. In this case, this is called a cold solder joint. It means the solder did not connect to both the lead and the solder pad. So watch, I'm going to trim these leads here, and what happens is the solder, because it's not connected to both the solder pad and the lead, basically has no connection any longer between the two. This can cause anything between a short connection between the two that works intermittently, or as you'll see in this case, the LED literally falls right out of the circuit board. To prevent this from being a problem, always touch the iron to both the solder pad and to the lead and feed the solder in from the opposite side. And the other common problem you may run into is the bridging of solder between two component legs. This can happen to both beginning and expert solderers. Do you see here how the bottom center and bottom left legs are soldered together? Here's how you fix that. Plug in your desoldering iron, keeping it away from anything you don't want to heat up. Then squeeze the red bulb so it can create suction inside the iron. Place the open-tipped end of the desoldering iron onto the lead with the excess solder, then release the red bulb to suction away the solder. Remove the desoldering iron from the lead and you should find that the solder has been removed. Then you can go back in with the iron and solder and repair the solder joint.
So let's jump right into it. For through-hole components in a circuit board, you'll want between 600 and 700 degrees Fahrenheit. That's 315 to 370 degrees Celsius. If you're soldering larger connections with more copper that's dissipating heat, then you may want a slightly higher temperature. With a temperature adjustable iron, you can see what works and adjust accordingly. Next, make your components stay in place without your help. This is where you can use your helping hands. If you're soldering a through-hole component in a Next, clean the tip of your iron. Use a brass sponge or a wet sponge to remove any oxidation or excess solder from the tip. A dirty tip is covered in metal oxides that transfer heat badly and can result in poorly soldered joints. Always remove excess solder because you'll only make reliable connections using fresh solder that has rosin in the core. Rosin acts like a flux when soldering, which eats away at the oxide layers that form on the surfaces of metals. Now we're ready to apply solder. The whole principle is to heat up your joint evenly and melt solder onto the joint, not the tip of the iron. Apply the iron to one side of the components that you're trying to join, and feed solder from the other side. The amount of time it takes to heat the joint depends on its size, the temperature, and the power of the iron. Tiny connections can take a few seconds, but large connections dissipate more heat and will take longer. Remember to make as much contact as possible between the iron's tip and your part. Hold the flat edge of the iron's tip against the joint, not just the point of the iron. Sometimes it helps to tin your iron by putting a small amount of solder on the tip, to bridge the air gap between the iron's tip and your components to create better heat transfer. When you're done, remove first the solder and then the iron. The joint will need a few seconds to cool, so don't disturb it. Last, check whether you made a good connection. Did the solder wet to both surfaces? Is the joint smooth and shiny? Is there too much or too little solder? On a printed circuit board, the first big no-no is putting a blob of solder onto your iron and trying to transfer it to your joint. This won't work because your flux burns away, and you're not ensuring that your workpieces get hot enough for the solder to properly adhere. Secondly, don't grab your joint while it's hot. I didn't burn my finger here, but I easily could have. Third, your workpiece is sloppy if your components aren't properly aligned. This example is of course exaggerated, but beginners often don't ensure that parts are properly mounted flush against the board before they begin.